So now let's look at how to utilize this mathematical induction to prove the divisibility of an expression. So this example here is show using mathematical induction that for any value of n, that is a positive integer, 7 to the power of 2n plus 16n minus 1 is divisible by 64. So let's first, using our mathematical induction rules, like we're using a very similar process to what we just used before. There's just like a few little steps that might help you sort of change how we're doing things a little bit to understand what is the general process of finding the proof, finding how to prove divisibility with mathematical induction. So let's first say let P n be the statement that we can write it like this as well. You might not know, but we can use a vertical bracket to, sorry, not a vertical bracket, a vertical line to say that 64 divides, that is 64 divides 7n plus 16n minus 1. So we rewrite the statement and then we do the basis step. We're following a very similar sort of system to last time, and that is the system of mathematical induction. Let's consider P1, because that is our minimum value of our well-ordered set of the positive integers. So we have P1, that is 7 2 times 1 plus 16 times 1 minus 1, which is the same as 49 plus 16 minus 1, which is equal to 64. So for our basis step, we know that it's true because 64 divides 64. Therefore, it is true for P1. Then we can do our inductive hypothesis. So we're going to assume true for PK, i.e. Now, with this inductive hypothesis, with divisibility, we can, first we can write sort of the same form that we did up here for n, but then we can write this same statement in a different form that's much more helpful to us. So we have 16k plus minus 1. Therefore, we can write the statement in a different way that says 7 to the power of 2k plus 16k minus 1 is equal to 64m, where m is an integer, is any integer. Now, what this is saying is this is basically the same statement. This is just saying that 64 is a factor of this, which is the same as saying 64 divides this. So based on this, we can finally do our inductive step. And we may as well do this on another slide. Step. For that, we are going to, again, consider PK plus 1. So that is 7 to the power of 2k plus 1 plus 16k plus 1 minus 1. So we want to prove that this is divisible by 64. Now, that means it equals to 64. This time, let's say n is a very bad one to do. Let's say t, where t is in integers. So we're going to basically try to prove that this is true. We're going to consider it. Now, to do that, I'm going to sort of expand this right side here to simplify our expression a little bit and get us just a bit closer towards finding an answer. So what I want to do here is I'm going to want to basically be able to, again, like last time, like we did over here, where we were able to substitute this into our equation to get an answer, to get a proof. We're going to want to substitute this into our expression here, and therefore we can get a 64m. And that is obviously divisible by 64, and then whatever's left should also be easily divisible by 64, because that's just how it tends to work out in these proof by induction of divisibility. So I'm going to keep expanding this out to make my life a little bit easier. That's times 7 squared plus 16k plus 15. Now that means we have a 49 times 7 to the power of 2k plus 16k plus 15. So since I want to basically have this expression here as part of this expression, I'm going to look at the easiest way to do that. And from my perspective, the easiest way to do that is to get a 16k and a minus 1 inside these brackets here. How do I do that? Well, and this is generally how the step that you're probably going to have to do for these proofs of divisibility. You're going to go write the equation down, and then you're going to add, since you want to get something in these brackets here, you're going to, let's say we want to get 16 in these brackets. How are we going to do that? Well, it's useful for us to add 49 times 16k, and then also subtract 49 times 16k. That means that what we can do is we can actually, since 49 is a factor of this, obviously, we can move the 16k into here, into these brackets. And then we have this on the outside, but we can worry about that later. Now we also want to get a minus 1 in there. So I'm going to do a minus 49 and a plus 49 at the end as well. So the equation is still equivalent. The expression is still equivalent to this expression over here. They're equal to each other, but we've put it in we've added some factors, we've added some parts, some terms that can allow us to move things around a little bit. So we have 7 to the power of 2k minus plus 16k, because I've moved the 16 in there. That means we can cross out all of that. Minus 1. That means we can cross out this. So then I have to write everything that still exists on the outside. And now we're at sort of a slightly better spot, and I'll show you why in a second. It's 49. Okay. So now what we can do is we have this here, which is exactly the same as this expression here. And we know that this expression is equal to 64m. We know that it's divisible by 64. So we can put 49 times 64m, and it's still equal. So we have plus, now we can move sort of these terms together. So we have a 16k, then we have minus 49 16k. So that equals to minus 48 times 16k. And then we have a 15 plus 49, which conveniently equals to 64. Now we have 64 outside of 1 from this value over here. And then we have plus 49m. And then outside here, we just have a minus 48 times 16k. Now, what I'm going to do with this is first I'm going to move it all the way up here. I'm going to divide this by 4 and times this by 4. So that leaves us with 64, 1 plus 49m minus 12 times 64k. So we can put everything in these brackets here, with these brackets with 64 on the outside. 49m plus or minus 12k. Now, this point allows us to immediately say everything must be divisible by 64, obviously, because we have that on the brackets outside, and m and k are both integers. So that means we have 64 divides 7 to k plus 1 plus 16k plus 1 minus 1. Now, that means true for pk plus 1 if true for pk. And that's because we did use our assumption we made over here of pk to then prove pk plus 1. So then we can write our final statement that we have to do for every mathematical induction. It always gives you a mark. Even if you can't figure out a mathematical induction, if you can just like sort of cheat and write this statement without actually ever getting an answer, like write something like this, you can often get half or a full mark in an actual exam. So we're going to write, we have shown true for n equals 1, sorry. And I'm writing it in a very different way than I'm doing it over here to make a point that you can write it in quite different ways, because it is just a statement that summarizes what you've done. So we have shown true for n equals 1, and if true for n equals k, then true for n equals k plus 1. Now, it would be good to write at the end, we have therefore proven true by mathematical induction. But I'll just do that. So that is our system of mathematical induction. It's complicated, and a lot of it just comes down to doing a lot of these questions over and over until you realize there are it sort of becomes intuitive, I guess, how to do them, because they are actually fairly surprisingly consistent how to achieve them. Like most of these divisibility questions, you're probably going to have to do what I did here. Basically, add these terms in so that I can put something into these, factorize something into these brackets here. So there are consistent methods of moving towards answers for these mathematical induction questions that you will only get good at when you have actually spent a fair amount of time doing these questions. They are questions that you will mainly learn, and you might not necessarily understand immediately, but the more you practice them, the more they will just sort of, the process will start to make sense to you. And I would say that more than any other type of question, basically. I'd say more than any other type of question in specialist maths, I think mathematical induction questions require practice and not just like an understanding.